Good morning, dear students. In the last module we had referred to units in general, and we wanted to know what is meant by a unit and a standard for measurement, and how it is designed, and what are various systems available, and how many units are necessary and how many are given in a system, how to write the units. All these things we have seen in the last module. In the present module we will try to know something more about these units further. One of the most important things with reference to the units is you may measure physical quantities in different units or different systems of units also. But when you write an equation in physics connecting these physical quantities, this equation should be consistent with the units. That means if you write any equation, for example, you write, say, some A is equal to B plus C something, where A, B, C are physical quantities. When you write an equation like this, by any process of derivation or any other method, by any concept, you arrive at some equation like this. This equation should be consistent with the units. That means the units of A should be that of units B and that of units C. All the three must have the same units, then only such an equation is possible. This sort of a concept is necessary for the units. Like, for example, suppose this A is distance. Its unit will be in meters, say. So the units of B also must be meters, the units of C also must be meters. That means B and C also must be physical quantities like distance, because you have to make an equation adding B to C to get A, which is a distance here. Then A as a distance can be obtained only if a distance called B is added to another distance called C. If B is force and C is distance, you can't add them. Force will have different units, the distance will have different units. So those quantities which you are adding here in the equation should have the same units, then only such an equation is possible. This consistency must be maintained in the equation. Further, you will see another example. Suppose there is some physical quantity P is equal to Q into R plus S by T. Suppose there is something like this, whatever they are, physical quantities. Here, this is a physical quantity, these two also may be physical quantities, this also may be physical quantities separately. But here, whatever be the units of P, here what we have here, and units of Q and R together, when they are multiplied here, you see, in the equation here, Q is multiplied with R. Q into R gives a new product. Product means new physical quantity comes from that. It is neither Q nor R. What comes out of them is something new. So that physical quantity will have a different unit. And that unit what you have, it will not have the unit of the Q, it will not have the unit of the R also. So that unit which you get for this product physical quantity should be the same as the unit of P. Here there is only one term, therefore we could know that this must be same distance as A. Here Q and R are two different physical quantities. Whatever they are, when they are multiplied, what product you get from them should be having the same unit as P here. Similarly, S is a physical quantity, T is another physical quantity, suppose. This S by T is another new physical quantity. It is the product of S into 1 by T. So just like here, there is a product here. This product is S into 1 by T. That is what it means. That is what this implies. Therefore, this physical quantity, the whole thing, as a product as whatever is coming up there, that should have the same unit as that of P again. That means just like here, P and this term here and that term here, all the three must have the same physical quantity, have the same units there. Such a thing only is possible. That consistency is to be maintained. That is one thing to be known. Another thing is, this equation what you are giving here, if you write this in CGS units, this also must be in CGS units, this also must be in CGS units. You can't write one term in CGS units, another unit term in the FPS units and so on, or in SI separately like that. Whatever you choose one system in writing the equation. All the physical quantities must be in the same system. And the units of each term in the equation on either side must be having consistently the same units. This is what is meant by consistency of units. That's what we are talking about now. We call it as unit consistency, we call it. Unit consistency. What is meant by this? It means if there is any physical quantities or a set of physical quantities which are involved in the relation, equation like that, each term on the equation, either side of the equation, should have the same units. Units must be of the same nature. They must be from the same system, and also the physical quantities, each one should have the same units. Such a thing is only possible as a physical content of equation. If any equation comes where such a thing is not matching, you can say that equation may be not totally correct. There must be something wrong in that, or there must be some hidden concepts which you are not able to explicitly see in the equation. Sometimes it happens like that. We shall see certain things like that in the example now. I take an example to tell you about that. Take a simple example like V is equal to U plus AT. I think you know this equation very well in your lower class itself. In this, V is velocity, final velocity. U is also velocity, we call it initial velocity. A is acceleration, T is time taken. When a body starts from a point, is moving like that, its initial velocity when T is equal to 0. Initially it is having a velocity U. Or sometime it reaches a point here, and there the velocity is V. And velocity has changed from here to there with what is called an acceleration equal to A. Time taken to come here. That is what the situation is explained in the equation here. The velocity that the body is obtaining at the end of the time T is given by initial velocity plus the product of acceleration into time taken. If this equation were to be correct, each term here must be having the same units. Then only it is possible. Let us check here. Velocity is having units. I am writing in SI here. It is meters per second. So then each term also must be expressed in SI units. So the initial velocity, which is U, must also be having units as meter per second only. Because this is also velocity, this is also velocity, we know they will have same units. Then what about A into T? A is having unit meter per second square. That is unit for A. For T time, it is seconds. It is multiplied by second. So this is what the multiplication. So what will it amount to? This minus 2, 1 plus there, it becomes minus 1 again. You can check now all the three quantities, all the three terms on either side have the same units. Such the consistency is expected to be there in the units. They should be there like that. This is what is to be borne in mind while you are working with it. This concept of consistency of units is better explained sometimes in a different way also. I will put that here. To explain this unit consistency, there is a concept that is developed what is called as dimension. There is what is called dimensions in physics for physical quantities. Just like physical quantities are having units, they are also given dimensions. What is meant by dimension? It tells you about what are the fundamental physical quantities in that particular physical quantity what you are talking about. Like for example, suppose you take mass. We said it is fundamental physical quantity. Mass can be expressed only as mass, nothing different. So the unit of mass is given a symbol called m. It is given like this. Unit of mass is given as m. We write like this. If you say the unit, the same thing can be expressed like this also. The dimensions of mass are m. We can say like that. Or we can say dimensional formula of mass, dimensional formula we call it. You can call that way also. It is m. Or we can write like this. If you call m as mass, show like this in the bracket. It means what you are talking is about dimension, and that is m. That's what it means. Similarly, dimensions for length, if you call it as L, is given as capital L. Similarly, dimensions of time, if you put like this, it is given as capital T. What is M? What is L? What is T? They are not simply dimensions. As definition, it is simple dimension. Dimension means it represents one unit. This m can be 1 gram, or it can be 1 kilogram, or it can be 1 pound, depending upon which system you are expressing it. But the symbol will be the same. Similarly, L can be 1 centimeter, or 1 meter, or 1 foot, depending upon which system you are expressing it. Time, of course, it is 1 second always. In all systems, it is the same. So, the symbols, what you are writing MLT, represents one unit of that system, whichever you are choosing. The power to which they are there will represent how much is there, the dimension in it. For example, if you write m, it is nothing but m power 1. That's what it means. That means mass has got one dimension in mass. This term m, whatever is there in this, has one dimension. Because m is mass dimension, so it is one dimensional mass. One dimension in mass. Similarly, length, one dimension. T, one dimension. Now you take, for example, density, or you take volume. Better if you understand this simply. Take volume. Volume is physical quantity which is made up of length into breadth into height, say. And this is also length, this is also length, this is also length. So if you write dimensionally, therefore, this is L, that is also L, that is also L. All the three are lengths only. So we have given the symbol L there. This L, if you write like that, mathematically you can write this as L cubed. Now L cubed becomes a dimensional formula for volume. If you call volume as V, we say like that. Dimensional formula for volume is L cubed. It means volume has got 3 dimensions in length. That is the meaning of that. Automatically you can now know the unit of this one. What will be the unit of this one? This means it is 1 meter cube. Because L means 1 meter, like what I said here. In SI, say. You put the same thing in CGS, it becomes 1 centimeter cube. Like that. So, this way of representing the physical quantity in terms of the dimensions is what is called as dimensional formula. We call like that. So, this dimensional formula you can now put for various physical quantities. For any physical quantity you can write dimensional formula now, depending upon its dependence on the basic things. So, only MLT are initially given the number, the symbols here. Take for example the next one. To understand this, take density, another physical quantity. Density we call it. What is density? It is mass by volume. That is what density means. So if you write dimensional formula for density, for mass we will write m, for volume we will write L cubed. Now this will be represented like this. Dimensional formula for density is equal to ml minus 3. We write like this. Dimensional formula always represented in power like this. So this becomes the power, that becomes the dimension also. Now how do we read this one? This is called dimensional formula for density. How do we read this? We read that density is a physical quantity which has got 1 dimension in mass and minus 3 dimensions in length. We say like that. That's how it has been designed. This concept is what is called dimensions concept or dimensional formula. This dimensional formula can be used in understanding the consistency of the equation. Like for example, you can write dimensional formula, a set of dimensional formula can be written. I write again for velocity. If you want to, will write one more. Velocity is displacement by time taken. You know the definition. Therefore, it is S by T. That is the formula generally we write. Coming to dimensional formula for this, displacement is L. Dimensional formula for that is T for time. So this will be Lt minus 1. Similarly for acceleration, dimensional formula you want Lt minus 2. Like that you can go on writing for any number. It all depends upon how much you know about the physical quantity there. For example, force, you say. Dimensional formula for force. Force is given as mass into acceleration. That is the equation it has. F is equal to ma. Newton's laws of motion, you know. F is equal to ma equation. That's what I am using. So when you write like this, mass has dimensions m, acceleration has dimensions Lt minus 2, like what I have shown here. So this becomes a dimensional formula for force now. Once you know dimensional formula like this, you can know the unit of the physical quantity also. Like for example, you see here in mass, in volume we have got here as 1 meter cube. So what about here? It is 1 kilogram per meter cube. That is the unit there. M means 1 kilogram. L to minus 3 means meter cube with a minus sign in the power there. So like that we find here also. For this one, it is 1 meter per second. We can write like that. This is 1 meter per second square. So like that, by knowing the physical quantity in the diamond formula, we can get its unit also like this, substituting the symbol with the unit there. Only thing is, you must take the unit from the same system for all the symbols what you are using here, for all the symbols you are using there. You must have same system of units involved. You cannot put one in meter here, another in a foot there, and so on. Like, can't put like that. You can't put this as foot and here second there separately. That will be different. So you must understand that like that. So let us see how to write these things. So this is the diamond formula for many things. You can write any physical quantity. Energy, you see, for example. Energy is work done. Work done is force into distance, displacement. Force has diamond formula, just now I wrote here mLT minus 2. Distance has diamond formula L. So energy diamond formula, what will be that now here? If you write like this, for energy, it will be M, L into L, L square, T power minus 2. This becomes diamond formula for energy now. So like that, any physical quantity, you can write dimensional formula. This is first to be remembered. How this diamond formula helps for the unit consistency, we will discuss next. Right? That is what the first thing to be known. Then, what is the principle based on which you are talking about all this consistency in dimensions? That is this. If you have got physical quantities involved in the equation, just like what you said earlier, if any equation is made, each term in the equation on either side of the equal to sign there, on either side, you must have the same dimensional formula. Then only that equation is valid. So you can check the correctness of the equation by using this one. Consistency of the units also can be known from this one. Like, I show you an example. I have taken the same example as V is equal to U plus AT, just now we have mentioned here. In this, if you write this equation dimensionally, V must have the same dimensions of velocity. You know, velocity is LT minus 1, diamond formula, and that means velocity's diamond formula is that. Similarly here, for U, also diamond formula is LT minus 1 only because it is velocity again. Coming to AT, for A it is LT minus 2, for T, for time it is T, so this is again LT minus 1. Now you can see each term in the equation on either side are having the same dimensional formula. So this dimensional formula being common, which is there for each term, the equation must be correct. If the equation is correct, this consistency must be there. This is what is called as homogeneity of dimensions, we call it. Homogeneity of dimensions. So if you want to have consistency in unit in the equation, homogeneity of dimensions also will help you to understand that. Even if you don't know the units completely, if you know diamond formula, you can talk about the consistency of the units there in that, whether it is consistent or not. So such things are there. So any equation which is correct physically will have this homogeneity principle obeyed. It does not mean suppose it doesn't obey this homogeneity principle, you cannot say the equation is wrong. Sometimes it is not possible to say like that. I give an example here. You can take another equation, S is equal to ut plus half at square. Distance travelled by a body in t seconds. When you see this equation, you will find diamond formula. If I write directly here, this is distance. On left side it is distance, displacement. So on this side it is LT minus 1 into t. That is this first term. The other term here is having half. Half is numerical figure. Only physical quantities will have dimensions. The numerical figures will not have dimensions. Therefore, there is no dimension for half. Dimension is there only for this one. So that is LT minus 2 and t square for time here. So if you see this is also L, this is also L. So dimensionally, each term is having the same dimensional formula. on either side. So this equation must be correct. So if the equation is correct, definitely dimensions will match there. Homogeneity is certainly obeyed there. You take another example from this only further. You take this equation, suppose the same equation you have here. Instead of half you have got here, say it is 3 by 2 you have got here, say. 3 by 2 also is a number. So when you check dimensionally like what we did now, you will find dimension of each term here will be L, here also L, here also L you will get. But 3 by 2 being numerical figure, it does not have dimensions. So this equation, whether it is totally correct or not, you cannot say. Because 3 by 2 is not having dimensions. So as for physical quantities are concerned, all right, but numerical factors we can't say. Therefore, we can't say the equation is completely correct. That means, if the equation is dimensionally right, you cannot say completely the equation is totally correct. Here, this equation is wrong. We all know it must be half here. It should not be 3 by 2. So like that, sometimes the dimension formula helps in knowing this homogeneity of dimensions, and thus we can check the correctness of the equations. We can only check the correctness by unit consistency, and those terms which don't have units there, numerical figures are etc. are there, then we cannot know about the correctness of the equation there. Anyway, the consistency of the units can be known from that. That's one thing. Second thing is, there are certain physical quantities which do not have units, which do not have dimensions also therefore. What are they? Take for example refractive index, we say. Refractive index of a medium, we show with the symbol mu. It is defined as sin I by sin R, where sin I is angle of incidence here, this is angle of refraction here. So this is a pure ratio, and this does not have any dimension formula, no units also for that. It's a ratio like that. So this physical quantity does not have dimensions, it does not have units. Similarly, we have relative density, another physical quantity. This relative density is ratio of two densities, density of a substance by density of water. So this is a ratio between two densities, therefore no units for this. No units, therefore no dimensions also. So such physical quantities, whether they are there in the equation or they are not there in the equation, your consistency of the units, your consistency of dimensions, homogeneity of dimensions, cannot say anything about them. That also should be kept in mind. You are talking about the units and dimensions, and when you are checking the equations. However, we can check the equations whether they are right or wrong as for physical quantities are concerned with the help of the dimensional formulae there. Then conversion. How to convert units? Conversion of units. Conversion of units comes because there are different systems of units also. Length can be expressed in feet, or it can be expressed in centimeters or in meters, etc., etc. Many systems are there accordingly what they are there. So if you want to convert the length, if you want to express in one system, there will be one figure, and the system there will be another figure, and so on. I told in the earlier module, a unit is expressed with the number and unit there. This is how we express physical quantity in units. Say 10 meters, we say like that. Suppose you want to express in centimeters, then what will you do? You put this 10, put this meter into centimeters. Centimeters means 100 centimeters becomes equal to 1 meter. So now this 10 meters becomes equal to 1000 centimeters. That means you have converted the length from the system where you expressed in meters to the system where you expressed in centimeters. When the number here, see, smaller number, larger unit. The same thing when it goes to other system which is smaller unit, number becomes larger there. So the conversion should be properly done there. It is already when you have got some simple quantities like this. You got more difficult quantities, then how do you do? We take an example for that. Suppose speed is there. We say it is some 36 kilometers per hour. Say the body is moving with a speed of 36 kilometers per hour. Some unit, some system, where distance is expressed in kilometers, time is expressed in hours. They write like this, kilometers per hour, or they write like this also sometimes, kilometers per hour. So they write like that. You want to express this into standard SI unit now. In SI unit we have got unit for speed as meters per second. You want to get into that conversion. How do you write like that? Take this 36, write kilometers convert into meters. 1 kilometer means, I was telling in the earlier module, 1 kilometer means, kilo means 1000 meters. So it is 10 cubed meters and divided by hour. 1 hour means 60 minutes. This is equal to 36 into 10 cubed meters, 60 minutes, and each minute is equal to 60 seconds also. Now when you write like this is 36 into 10 cubed by 36 into 10 square. This is 36 into 10 square meter per second. Now this is therefore equal to 10 meters per second. That means if a speed you express as 36 kilometers per hour, if a vehicle is moving like that, covering 36 kilometers per hour, the speed at which it is covering is 10 meters per second, we can say. Converting kilometers per hour into meters per second now. So in the conversion, we have gone to the units what they are, and their equivalent conversions where we want to take, we have taken, accordingly we brought into that system there. Then we have simplified the whole thing. That's what the method we have followed here. There is another way of doing it. In doing this conversion, the units can be considered as new mathematical quantities like thing. I was telling in the earlier module also, if you say it is 10 meters, it is 10 into 1 meter. That's what it means. This is a physical quantity measured as a mathematical thing here. So you can use this as 1 meter as a mathematical thing there. For example, I will put here, say, you want to convert this 36 kilometers per hour. We have got this. That means 36 kilometer by 1 hour. That's what this means. You want to convert this into meters per second, suppose. Then how to do it? Another way of putting it is put 36 number as it is. You want to have meters, not kilometers. So kilometer must be finished, it must be destroyed. So therefore put in the denominator 1 kilometer and put its equivalent to meters in the numerator. And what will be 1 kilometer? It is equal to 1000 meters. Because 1000 meters is equal to 1 kilometer, if you multiply with this ratio here, you are not changing the value of this by any chance. It is just like that. So this is equivalent to that. This is, because these two things are equal, they can be mathematically cancelled. So there is nothing wrong in that. The value of this ratio is equal to 1 only. So you can see like that, even per hour. You don't want to have hour. What is that you want to have? Seconds you want to have. So put kilometers. 10 cubed meters by 1 kilometer. And you want to have seconds. So right here, equivalent number of seconds. 1 hour. How many seconds will be there? Or to first step we want to take it as 60 minutes is equal to 1 hour. Take like that. If you want another step to understand only, I am putting all this. Once you get practiced, you can write quickly and know the values. 1 kilometer into 60 minutes. These are minutes. You don't want to have minutes here. So write minutes, divide by minutes. This 1 hour is there. Write here the minutes. What is the number of equivalent to 1 minute in seconds? 60 seconds. Put 60 seconds here. So now this 1 hour has been replaced by, this has been replaced by that minute. So now you see, originally 1 hour is here. Repeat here. So now this 60 minutes by 1 hour, they are in the denominator here. 1 hour was in the denominator here. So you must put the inverse sign here. That means you will write here as 1 hour by 60 minutes. Then come to seconds further. Next equivalent is 36 kilometers, 10 cubic meters, kilometer here, 1 hour. This 1 hour is originally there. And the 60 minutes. This 60 minutes now converted into seconds. So this is 60 into 60 seconds, 1 minute. 1 minute by 60 seconds. So we have put that ratios which are equivalent. 1 hour is equal to 60 minutes, 1 minute is equal to 60 seconds. We have put accordingly and put it here now. So then what happens? The kilometer gets cancelled here, the hour gets cancelled here, the minute gets cancelled here, and you are left with this. What is this here? It is the same thing as 36 into 10 cubed by 36 into 10 square meter here, second denominator there, so comes as meter per second. So this once again the same as 10 meters per second. So one way of converting it is by knowing direct conversions, or by representing the unit which you does not want to have in an equivalent ratio like this. Every time go on putting it like that, and then gets the things which are not wanted to get cancelled, and leaving only those quantities which are required there. So if you represent like that, the conversion of units can be done. That's one way. Another way of converting units using the dimension formula also is there. That is also maybe simpler sometimes. We will see that here. In this, what we do is we go with the dimension formula. Suppose you want to know, I put the question like this. Sometimes you can write question also. How many newtons are there in one dyne? Say, question comes like this. That means you are trying to convert Newton, a conversion between, you are trying to convert the units of force from newtons to dynes, or from dynes to newtons. Accordingly, question might come like this. Whether it is newton or dyne, it is force unit. Therefore, what happens is the dimension formula will be the same for force. Dimension formula for force, that must be known first. We know it is LT minus 2, say. That is the force dimension formula. This dimension formula, if you represent in SI units, it gives Newton. If you represent in CGS units, it gives dyne there. So we write like that: M1, L1, T1 minus 2, suppose you say like that. Here, this can be 1 gram centimeter per second square. This is nothing but one dyne. If you do same thing as in SI units, giving us different suffix here. Suppose you are putting SI units there. This will be 1 kg meter per second square. If it comes out like that, this is actually to be written like this anyway. This comes out as 1 Newton. So if you represent this MLT in CGS units, you will get dyne. In SI units, you will get Newton there. We have to find out how many newtons are there in one dyne. So let us say like this: 1 M1 L1 T1 minus 2 is equal to N times M2 EL2 T minus 2. We say like this. What does this mean? This means dynes. This means Newton. Just now what I showed you here. Now we have to find the value of N. That's all what we have to do. How do you get N here? Write the equation M1 mathematically, M1 by M2, L1 by L2, T1 by T2 with a minus sign there. This is how it comes. Now substitute here. What is meant by that? M1 means gram. So write here 1 G. Gram generally written as G only, M need not be written there. Then this is 1 kg. M2, SI unit. L1 is 1 centimeter. L2 is 1 meter. T1 is 1 second. T2 also is second only. With time we don't have much complication. It is all the same in every system. So they get anyway cancelled here. What is remaining is 1 gram. Put conversion, either put grams into kilograms or kilograms into grams, as you like it. It is easier probably to put here. This is nothing but 1000 grams. Similarly, 1 centimeter, 1 meter means 100 centimeters. Now this will tell you the gram gets cancelled here, centimeter gets cancelled here. Because units are used like mathematical terms only, I told you. You can cancel them like that. You are left with 1 by 10 power 5. That means it is 10 power minus 5. Now come to the dimensional equation here. That means if you rewrite this equation in the words what is given, it means 1 dyne is equal to 10 power minus 5 Newton. That's what the equation means. You can see that. So like that, the dimension method also helps us in converting the units from one system to another system. Either directly knowing the conversion from the units, or writing it from dimension formula also can be done. Either way it can be done. Some examples are given there in your book. You can go through it accordingly. You can try to find out dimensions of physical quantities on one hand, check the correctness of the equations by checking the consistency of the units there, and then you can also convert one system of units onto another system of units by any of these methods that is suggested here. Thank you.